we'll see what happens. So we're talking about alkyl halides. Oh my God, pink pen or purple. I guess we'll leave it like that for a while. So alkyl halides, and I think it is recording. That's good. All right. So with the nomenclature, it's kind of very simple. It's kind of like the methyl ethers that we have done. Now you just have the halogens on there. So for example, if you had CH3Cl, this would be chloromethane. If you had CH2Cl, Br, so two hydrogens are substituted. In this case, it would be bromo. Okay, it's telling me that my internet is unstable, okay? And it's possible because I'm recording also, but we'll see. If I go out, I will come back, I promise you. Okay, bromo, chloro, methane. Just make sure that you follow the alphabetical rule, okay? And then if you had more, like a long chain, and then you had chlorine on there, you'll follow the same rules. So this would be 2-chloro, 1, 2, 3, 4, 5. So 2-chloropentane. No space, okay? I happen to leave a space, and I'll take it off actually, but there is generally no space in between. So 2-chloropentane, that's how it would be. If you had a methyl and a bromo, let's say you had something like this and you had a bromo. So in this case, nothing takes priority over the other. So alkyl groups have no priority over halogens. So you will just go by branching. Okay, so go by branching. And then after branching, you go alphabetical. So branching is closed in both cases. It's 2. So whether it's 2-methyl or 2-bromo. So because the branching is 2, we're going to go ahead and take it alphabetically. So 2, 3. So 2-bromo, 3-methyl, and then this is butane. Okay, so something like that. So which means that the alkyl groups, methyl, ethyl, propyl, all of these, they have no priority over halogens. You treat them both equally, especially since if you're deciding, you know, where to start the branching from, it's whatever is closest to the branching, that's where you go. For cyclic compounds, same thing. So if you had something like this, this will still be 1-chloro, 1-methyl, cyclohexane. Again, nothing really new over here. Okay, so just remember to number everything. Remember to find the longest chain. If you have the straight chain compound and cyclic compounds, you have to start the numbering from wherever the substitution is. Okay, and again, if they were in 2 different places, so for example, if you had chlorine here and then you had an ethyl group here, that's fine, no problem, since chlorine is alphabetically first. So 1, 2, 3, so 1-chloro, 3-ethyl cyclohexane. Now, in this case, you don't know whether it is cis or trans or anything like that, but if that is given, please make sure you write that, okay, whether it's cis or trans. So I noticed that in your homework, when you did your stereochemistry homework, and I asked you to write the names in there, there were still some issues with the chlorines and whatnot, but it's not that hard, okay? Now, when you look back at it, you will probably think, oh, I don't know how I missed it, okay? Because it's really pretty straightforward. Some of the compounds, they actually have general names, all right? So I'm going to talk about that for just a second. So for example, when you have something like CH3Cl, okay, so I already wrote that name before. So this was called chloromethane. So this is actually, if you wanted to give the classification of the entire group, this would be haloalkane. These can also be called alkyl halides. So in this case, you're naming the alkyl group first, which is the methyl. So methyl chloride. Both names are fine. This one is general. Okay, the alkyl halides, these are general names. The haloalkane is the IUPAC name. Anything that is IUPAC will always end with how many carbons you have, okay, which is 1 in this case. So we do have some general names, which means that if you had 2 carbons, it would be ethyl chloride or propyl chloride. You can say all of those, okay? And so if you have something like this, I don't even know why I keep taking chlorine. I can take bromine. Let me go ahead and take bromine, okay, instead of chlorine. So if this is bromine, so now you have 2 different names possible, okay? So 2-bromopropane. And then look at this, okay? This is like a fish, right? Like a fin of a fish. So this is an isopropyl group. So this would be then isopropyl bromide. That would be the general name for this. And you have to know these, by the way, okay? Because I can give you either general name or I can give you an IUPAC name. You have to know all of these, okay? So isopropyl bromide or T-butyl chloride, T-butyl iodide, whatever it is, you have to know all of these, okay? So whatever alkyl groups you know, you have to know their halides as well. Again, not too hard because you should already know your alkyl groups, okay, by now. Okay, so then still continuing on with the general name, we have CH2Cl2. So CH2Cl2 would be dichloromethane. The general name for this one is methylene chloride. Methylene chloride. So I want to talk just a little bit about the methylene, okay, because this is a weird one. We have not seen this one before. So you have the methyl chloride, which is CH3Cl, right? That's an easy one because we know what a methyl group is. But the methylene group is actually the CH2 group, okay? That's the methylene group. So how does it come about? So think about all the structures we have been drawing. So for example, if you go from ethane to propane, you don't have to write this out if you don't want to, by the way. You add a CH2 group to that. If you go from propane to butane, you add another CH2 group. So now you have 2 CH2 groups. These CH2 groups are what are called the methylene groups. Individually, they are called methylene groups. But in the case of butane, since you have 2 of them, this will be called ethylene. So 2 methylene groups. I don't want to put dash because you would think dash is nomenclature, but it's not dash that way. So you have 2 methylene groups, or you have 1 of the ethylene group. Okay, so this is kind of a general nomenclature that's been coming on from a long time, so we still use it. So when you go in the lab, okay, and this is really a lot more common in the lab than anywhere else, is you might see the bottle for dichloromethane labeled as dichloromethane, or it could be methylene chloride. Okay, so depending on the nomenclature system in the lab, it depends on that. So, but anyhow, that's what methylene chloride is. It could be methylene bromide, by the way. Bromide would just be 2 bromines in there. Iodide would be 2 iodines in there. That's all. So then the CH, Cl3, and this is trichloromethane. And if you're wondering why am I writing all of this, is because the general name for this one is chloroform, which is something that we have heard of. I mean, if not heard of, at least seen in the movies, because that's what they use all the time for kidnapping people or putting people out. So that's chloroform. So chloroform, again, if it's 3-chlorine, it's chloroform. If 3-bromine, it will be bromoform. If it is 3-iodine, it will be called iodoform. So you just change according to the halogen. Okay, so, but the form remains the same, whether it's chloro or bromo or whatever it is, okay? So trichloromethane, that's the IUPAC name. Chloroform is the general name. Again, in the lab, you don't know how you will find it, so you need to know both. CCl4 is tetrachloromethane, and there is no general name for that. And I think you are probably taking a sigh of relief now. So, okay, I'm done with this. So this is your basic nomenclature, okay, for all the halides. Not all the halides, obviously, we can't cover all of them, but just the basic fundamentals, okay? It's not all that different. Stop me, okay, wherever you want to, if any of the rules are not clear to you. Okay, so one last thing I want to mention before I move on is, let's say that you have something like this. I wrote in my email also for you that you need to still know the primary, secondary, and tertiary. So this is primary, this is secondary, and this is tertiary halide. And why is it primary? Primary bromide is primary because of the connection points, okay, in there. So the connection point for this bromine is connected to 1 carbon. In the case of secondary, it's connected to 2 carbons. In the case of tertiary, it's connected to 3 carbons. That's why it's tertiary. In this chapter, oh my God, we will be talking about primary, secondary, tertiary so much. Okay, so if this is something that's not clear to you, either it will become clear or you need to make it become clear for you. Okay, so you need all of this. So you can, you know what you can try and do is go back to chapter 2, because that's where we learned the primary, secondary, and tertiary, and see if any of that helps you, okay, with the with this. Okay, and if not, then let me know. I can help you more, because this is not something that you should miss at any point. Okay, so I just want to talk a little bit about physical properties. So physical properties, of course, the first thing we talk about is melting point and boiling point. Does anybody want to take a guess as to what the physical properties might be? Like, not the physical, the melting point. Do you think it will be higher than alkane or less than alkane? So compare it to alkanes. What do you think? So if these two were what you were comparing, which one is going to have a higher boiling point? I'm going to, because chlorine has a higher electronegativity. Okay, so remember, anything to do with melting point, boiling point, these things have to do with intermolecular forces. I was just going to be happy if somebody said IMF, you know, intermolecular forces, but this more specific, I would have asked you for the most specific intermolecular force then, which is dipole then, okay, in this case. So yeah, any kind of a halide is actually going to have at least a little bit of dipole forces in them. And so because of the dipole moment, you're going to have intermolecular forces. So chloromethane, which has only 1 chlorine, you know, instead of the 4 hydrogen, even this one is a liquid, when we know methane is a gas. All right, it takes up to 4 carbons. We get to butane, and then we turn into a liquid, not we. Butane turns into a liquid, but chloromethane is already a liquid. Okay, so dichloromethane is also a liquid. Okay, and that's why I said you will find it in the lab, because dichloromethane is a liquid. So it's not that we don't have gases, but not at this level. Okay, we don't deal with gases so much. So dichloromethane you will find. But anyhow, so all of you have to look at the corresponding thing. Okay, and the other thing also you have to watch out for is how many chlorines there are. So if there was 2 chlorines, so CH2, Cl2, versus CHCl3. Now, excuse me, CH3Cl. Now this one is going to be more because now you have 2 chlorines in there. So you have even more dipole moment. And to the point of what Lucas was saying, so it's not about the size. Lucas, I don't know if you mentioned the weight in there, but the weight is also more. Okay, I think you did. Okay, so yeah, exactly. So the weight is also more, and now the dipole moment is more. So now you have 2 or 3 factors working here. The weight generally doesn't do a whole lot for melting point, boiling point. The weight actually does a whole lot for density. Okay, so let's talk about solubility first, and then we'll deal with that. So solubility in this case is going to be very slight because you have the dipole-dipole forces, but you don't have hydrogen bonding, okay? So, and the dipole moment is also kind of strong. It's not like hydrogen bonding as in like fluorine. So, but the fluorine also has to be bonded with hydrogen in order to have hydrogen bonding. So that's not happening, okay, in here. So the solubility is actually no. And the solubility in what? Solubility in water. Okay, so pretty much it's a no. Okay, and if it is, then it's so light that it doesn't even matter. Okay, and so for all of you who are in the lab, you must have already used dichloromethane for extraction purposes, and the water actually starts smelling a little bit. It may not have any dissolved dichloromethane, but it does smell. Okay, so you can tell that, yeah, okay, you know, it's been somewhere. So solubility is no. And so because the solubility is no, now we need to talk about density. And so density, because of chlorine, so now the heaviness actually plays a role. So now this is going to be higher than water. So because of the chlorine and iodine and bromine, all of these are heavier atoms, the density is going to be higher than water. In the lab, this is a very important thing because we use dichloromethane a lot as a solvent. And so if you're dealing with solvent, the other most common solvent is water. So when you're dealing with dichloromethane and water, you need to know how to separate them. So if they're not soluble, it's a great thing. But okay, fine. So you will end up having 2 layers. And so in a test tube, if you have 2 layers, then which one is which? So you now know that the dichloromethane is actually the bottom layer and the water is the top layer. Okay, so alkanes were the other way. Remember, alkanes were lighter than water, so they will be the top layer, but haloalkanes are heavier, okay, than water. So you have to remember these densities. I don't know if your professor has you write physical properties or not of all of these molecules. I do in my lab. So that way you know what the density is going to be. So that way you can predict whether the solvent is going to be above water or below water. Okay, that way. So these are the 3 properties. And the last one we always talk about, of course, is odor, which is the smell. And the smell is kind of sweet. It's not bad, let me say. Whenever I say sweet, it means that the smell is actually not bad. Although I will not recommend anyone smelling chloroform unless you want to be out. Okay, so yeah, don't smell any of these things. And actually, one of the things I want to mention to you about all these haloalkanes, especially chlorine. Chlorine is a little bit different, okay, because it's kind of polar. It's heavy, but not that heavy. So, you know, you have fluorine, chlorine, bromine, and iodine. Iodine is too heavy, right? It's the bottom of the periodic table. So it's very heavy. So we generally don't use iodine as solvents. And the same thing with bromines. We don't use bromines as solvents because they also have very high boiling points, okay? And so we use chlorines a lot more. So you will see dichloromethane, you will see chloroform as solvents in the lab because they're very doable. They dissolve all the organic compounds really well, and then you can get rid of those solvents also very well. But the problem with all of these is that they're very potent carcinogens. Okay, and I don't think I need to use very in front of it. A carcinogen is a carcinogen, which means that they cause cancer. Okay, so you have to be careful. So let me write some of the applications also. So applications we are talking about, and the first application is as a solvent. So in the lab, you find it all the time, whether it's in the lab or in industry, people like to use these solvents because they dissolve, as I said, organic compounds really well. They have low boiling points. So for example, dichloromethane, I think, is either 42 or 46 degrees Celsius. So which means on a hot day, it could be evaporating already, you know, so it's easy to get rid of. But of course, the big problem is that it is a carcinogen. So that is something you have to watch out for, you know, for halogens. Then other applications of halogens are there actually quite a lot. And a lot of them are not so practical that you don't see them, okay? Because a lot of times they're actually used as precursors for other things. I don't even know what the spelling of precursor is. Is it an ER or OR? You guys figure it out. Precursor for other molecules. So what does this mean? It means that if you want to synthesize something, you start with an alkyl halide. So the alkyl halide itself doesn't stay, you know, that much. You will, because this chapter really, that's all we are doing is also we're going to do a lot of reactions. So that's what happens. So they're a precursor for other things. Okay, so solvent is the big thing. Then we use them as starting materials. So, but you have to be careful, okay? And again, you can write somewhere if you want to, but they are carcinogens, okay? So one has to be really careful when you're working with any kind of a halide, especially the chlorine one, okay? Chlorine one, why? Because the bond actually breaks easily. Now, if you remember in chapter 6, I told you not to look at the bond energies because you don't really need it so much yet. We'll be dealing with that at the end of the semester, okay? So that's where actually you will find the bond energy, and the bond energy of chlorine is it's pretty doable, okay? So which means doable means that you can break it quite easily, okay? So we have to be very careful. One of the problems that we encounter with some of these chlorinated compounds is that they've been around for a long time as, what do you call, coolants. So when you have a can of something, okay, so for example, you have a can of hairspray, and when you press that hairspray, when you press that button on the top, you have to feel the can. Next time you do this, okay? Feel the can and you will feel that it's going very cold, okay? And why is that? And that's because there is a coolant in there, which is keeping your hairspray at, you know, at a cooler level, at a level that you can use it, okay? Because the hairspray is coming out sort of like a gas and sort of like a liquid. So they're very good coolants. In the fridge, you use them as a coolant, okay? In your car, you use them as a coolant. How? Because those are the AC, okay? Whatever liquids you put in the AC, those coolants, which are called freons. So freons is what you put in all of these coolants, or these are the coolants, and they're really, really bad for the environment. So I will talk about that at the end of the semester as to what happens to them, but just to give you an idea, the ozone layer in the stratosphere, that was all destroyed by freons only, okay? So now there is a treaty between all the developed countries, I think 5 or 6 of them, is called the Montreal Protocol. And according to them, you are not supposed to be using freon. So they have alternatives. I mean, we still have AC after all. So they have alternatives. So they don't use the chlorofluorocarbons anymore, CFCs, that's what they were called. So they don't use chlorofluorocarbons, okay? So you use other chemicals. They're still not very good though, okay? And just you can walk into any grocery store, Walmart, Publix, any grocery store, okay? And you just have to walk by the fridge and you have to walk by the freezer to just feel how cold it is and how much coolant they're using. So one of the biggest environmental challenge, or one of the biggest chemical challenge, is to figure out a way to cool all of these things without having chemicals in the atmosphere, which will destroy the ozone layer or which cause global warming, okay? And global warming has a lot of issues, but we're not going to get into that right now. But this is some of that, okay? So the CFCs are actually a lot of cause for some of these problems. And of course, they are carcinogens, oh my God. But they are so good, you know, I mean, they work so effectively that it's very hard to get, you know, get rid of them or to get out of it. one of the most common mosquito repellent DEET was also, not DEET, it was something else. That was also a chlorinated compound, and then they stopped using it because, again, it was more of a carcinogen. Obviously, if something is killing mosquitoes, it can also kill you in a different quantity. Okay, but anyhow, so this is some of the things about halogenated substances. Any questions, any comments you would like to make? Okay. All right. In that case,